September 1940. Inglewood, California. North American Aviation Factory. Edgar Schmued stood in front of a blackboard covered with equations and sketches, staring at a problem that was driving him insane. The German-born engineer had just 120 days to design an entirely new fighter aircraft for the British Royal Air Force, a fighter that would need to be faster, longer-ranged and more deadly than anything currently flying. But there was one problem that threatened to kill the entire project before a single prototype could be built: the radiator. Every engineer in 1940 knew the fundamental truth about piston engine fighters: the cooling system was a necessary evil. The massive liquid-cooled engines that powered high-performance aircraft generated enormous heat that had to be dissipated, and that required a radiator, a heat exchanger filled with coolant that absorbed engine heat and released it to the air flowing past the aircraft. But radiators created drag. Enormous, speed-killing, range-reducing drag. The faster an aircraft flew, the more air resistance it encountered, and radiators were like putting up a wall in the airstream. Engineers had tried everything to minimize the problem. The British Supermarine Spitfire buried its radiator under one wing, creating an asymmetric drag that pilots had to constantly compensate for. The German Messerschmitt Bf 109 hung its radiator under the fuselage in a bulbous fairing that looked like the plane had swallowed a bathtub. The earlier American P-40 Warhawk mounted its radiator in the nose, creating a distinctive shark mouth air intake, but also creating so much drag that the aircraft was notably slower than its European contemporaries. Every solution was a compromise. Every design accepted that the radiator would slow the aircraft down, and engineers simply tried to minimize how much speed they lost. The radiator drag was considered unavoidable physics. You needed to cool the engine, cooling required airflow, and airflow through a radiator created drag. It was thermodynamics, it was aerodynamics. It was an immutable law of aircraft design. But Edgar Schmued was about to prove that sometimes the laws everyone accepts as immutable are actually just problems nobody has solved yet. North American aviation had been approached by the British Purchasing Commission in early 1940 with an unusual request. Britain was fighting for its survival against Nazi Germany, and the Royal Air Force desperately needed more fighters. The British had asked North American to build Curtiss P-40 Warhawks under license, essentially to become a second production line for an existing American fighter design. It seemed like a straightforward manufacturing job that would bring North American steady work and revenue. But James Dutch Kindleberger, president of North American Aviation, had a different idea. Instead of building someone else's already obsolete design, why not design and build a completely new fighter that would be superior to anything currently flying? It was an audacious proposal. North American had never built a fighter aircraft before. Their experience was in training planes and medium bombers. The company had no fighter design expertise, no proven track record, and no prototype to show potential customers. And Kindleberger was proposing to design this revolutionary new fighter in just 120 days, 4 months from contract signing to first prototype. It was considered impossible by industry experts. Fighter development typically took years. The Spitfire had taken over 4 years from initial design to first flight. The Bf 109 had taken 3 years. Even the relatively simple P-40 had required 2 years of development. But the British were desperate enough to take the gamble. If North American could actually deliver a superior fighter in 120 days, it would be a miracle that could help save Britain from Nazi conquest. If they failed, the British would simply place the P-40 license production order they had originally intended. On May 29, 1940, the contract was signed. North American Aviation had until late September to deliver a prototype of an aircraft that didn't yet exist. Edgar Schmued was placed in charge of the design team. Born in Germany but emigrating to the United States in 1925, Schmued brought European engineering sophistication combined with American innovation and practicality. He had worked for several aircraft companies and had studied the latest aerodynamic research coming out of NACA, the National Advisory Committee for Aeronautics, the predecessor to NASA. Schmued was particularly interested in recent research into laminar flow airfoils, a revolutionary wing design that promised to dramatically reduce drag if it could be manufactured to sufficiently precise tolerances. But before Schmued could design revolutionary wings, he had to solve the radiator problem. Every calculation showed that the new fighter, designated NA-73 by North American and eventually named the Mustang, would need an extremely powerful engine to achieve the performance the British required. North American had selected the Allison V1710, a liquid-cooled V12 producing over 1,100 horsepower. This was a massive amount of power, and it generated a correspondingly massive amount of heat that needed to be dissipated. Traditional radiator placements wouldn't work for what Schmued was envisioning. A nose-mounted radiator like the P-40s would create too much drag and would interfere with the laminar flow wing he wanted to use. Wing-mounted radiators like the Spitfires would create asymmetric drag and would complicate the already challenging task of manufacturing laminar flow wings to precise tolerances. An underwing radiator like the Bf-109s would create enormous drag and would be vulnerable to ground strikes during takeoff and landing. Schmued needed to place the radiator somewhere that would minimize its impact on the aircraft's performance. And then, while reviewing NACA research papers, he found something interesting. A 1935 paper by a British engineer named Frederick Meredith titled "Cooling of Aircraft Engines," with special reference to ethylene glycol radiators enclosed in ducts. Meredith's paper proposed something that seemed to violate common sense under the right conditions. A properly designed radiator installation might create zero drag, or possibly even produce thrust. The idea seemed absurd. How could a radiator, which by definition blocked airflow and created resistance, somehow create forward thrust? It violated everything aircraft designers thought they knew about cooling systems, but Meredith's mathematics were sound, and they were based on fundamental thermodynamics. The key insight was this: air entering a radiator duct would be moving relatively slowly, because the duct opening would slow it down. As this slow-moving air passed through the radiator, it would absorb heat from the engine coolant. Heated air expands, it occupies more volume for the same mass. If the exhaust duct was properly shaped, this expanded heated air could be accelerated as it exited, potentially exiting at a higher velocity than it entered. If you could accelerate the air to a higher exit velocity than entrance velocity, you would be creating thrust, like a very simple jet engine. The heat energy from the engine would be partially converted to kinetic energy of the exiting airstream. In principle, if the system was designed perfectly, the thrust from the accelerated exhaust could completely cancel out the drag from the intake, resulting in zero net drag. In theory, with an exceptionally efficient design, you might even produce slight net thrust. Most engineers had dismissed Meredith's paper as interesting theory that would be impossible to achieve in practice. The tolerances would be too tight, the duct design too critical, the potential gains too small to justify the development effort. It was easier and more practical to simply accept that radiators created drag and to minimize that drag through conventional means. But Edgar Schmued saw opportunity where others saw impracticality. If Meredith's effect could be achieved, even partially, it would give the Mustang a significant speed advantage over any fighter that used conventional radiator installations. And Schmued thought he knew where to put the radiator to maximize the effect underneath the fuselage behind the cockpit, in a carefully designed ventral scoop. This location offered several advantages. First, it was in a relatively low-drag area of the fuselage underneath and behind the cockpit, where the airflow was still relatively smooth, but where a scoop wouldn't interfere with the critical forward fuselage aerodynamics. Second, it would be low enough to receive relatively cool air from below the aircraft rather than the hot boundary layer air from the fuselage surface. Third, it allowed for a single symmetric installation rather than split installations that could create asymmetric drag. And fourth, most importantly, it provided the length needed for a properly designed Meredith effect duct. The key to making the Meredith effect work was duct design. The air intake had to be carefully shaped to slow incoming air efficiently without creating turbulence. The radiator core had to be efficient enough to transfer maximum heat with minimum pressure drop, heating the air as much as possible without blocking flow. And the exhaust duct had to be precisely designed to accelerate the heated expanded air to maximum velocity as it exited. Schmued and his team designed an intake scoop that was relatively small and streamlined, positioned on the underside of the fuselage approximately under the cockpit. The scoop was carefully contoured to capture air from the relatively undisturbed flow beneath the aircraft and to decelerate it smoothly without creating shock waves or turbulence. Inside the scoop, the air would pass through a diffuser section that gradually slowed and compressed the air before it reached the radiator. The radiator core itself was positioned at the widest, highest pressure point of the duct. The cooling air would pass through the radiator at relatively low velocity, slow enough that it spent maximum time in contact with the radiator surfaces, absorbing maximum heat. The coolant flowing through the radiator from the engine would transfer its heat to the passing air, and the air would be substantially heated in the process. After passing through the radiator, the now heated air would enter the exhaust section of the duct. This section was carefully designed as a converging-diverging nozzle, basically a simplified jet engine exhaust. As the heated air flowed through this section, it would be accelerated, converting the thermal energy it had absorbed from the radiator into kinetic energy. The faster the aircraft flew, the more air would flow through the system, and the more pronounced the effect would become. The mathematics suggested that at cruise speeds around 350 to 400 miles per hour, the Mustang's ventral radiator system could approach zero net drag. The thrust from the accelerated exhaust would nearly equal the drag from the intake and the radiator core itself. At higher speeds there was even the theoretical possibility of net thrust, though Schmued was conservative enough not to count on that in his performance calculations. The oil cooler and intercooler for the engine's supercharger were also integrated into the same ventral scoop, positioned behind the main radiator. This meant all the aircraft's cooling needs were handled in a single optimized installation rather than being scattered around the airframe, creating drag in multiple locations. The design was elegant, but it was also risky. If the duct design wasn't precisely correct, the entire system could create more drag than a conventional installation. If the radiator core didn't transfer heat efficiently enough, the engine would overheat. If the exhaust section didn't accelerate the air properly, all the theoretical benefits of the Meredith effect would be lost. And all of this had to be designed, built, and tested within the 120-day deadline North American had committed to. While Schmued's team worked frantically on the radiator installation, they were simultaneously developing the rest of the aircraft. The wing was a masterpiece of aerodynamic design, a laminar flow airfoil that was thinner and more precisely shaped than any fighter wing that had been built before. The theory behind laminar flow was that if the wing surface was smooth enough and precisely enough shaped, the boundary layer of air flowing over it would remain laminar, smooth and organized rather than becoming turbulent. Laminar flow created dramatically less drag than turbulent flow. The challenge was that laminar flow was extremely sensitive to surface roughness and shape precision. Rivets, panel joints, paint imperfections, even dead insects could trip the boundary layer from laminar to turbulent flow, destroying the low drag properties. The wing would need to be manufactured to tolerances that were unprecedented in production aircraft, surface variations measured in thousandths of an inch, rather than the much looser tolerances typical of 1940s aircraft manufacturing. North American invested in new manufacturing techniques and quality control processes to achieve the required precision. The wings would be among the most precisely manufactured components in any mass-produced aircraft of the war. Combined with the optimized radiator installation, the Mustang would have less drag than any contemporary fighter, if everything worked as designed. The first prototype, designated NA-73X, was completed in September 1940, just 117 days after the contract was signed, 3 days ahead of schedule. The speed of development was unprecedented in aviation history, but the achievement meant nothing if the aircraft didn't fly and didn't perform as promised. On October 26, 1940, test pilot Vance Breeze took the NA-73X up for its first flight. The test was brief, just a few minutes in the air to verify that the aircraft was controllable and that all systems functioned. The landing gear had been left extended for this first flight as a safety precaution. If something went wrong, Breeze didn't want to be troubleshooting landing gear problems while dealing with other emergencies, but nothing went wrong. The Mustang flew beautifully. Controls were responsive, stability was good, visibility was excellent. Breeze landed after just a few minutes in the air, grinning. "This is going to be a hot ship," he told the gathered engineers and North American executives. He was more right than he knew. Over the following weeks, test flights continued and expanded. the landing gear retracted properly, revealing the clean lines of the Mustang's design. Speed increased as pilots gained confidence in the new aircraft. And then the performance data started coming in, and engineers began to realize they had built something extraordinary. The Mustang was fast, very fast. Initial tests suggested a maximum speed around 380 miles per hour at altitude, competitive with the best fighters currently flying. But as testing continued, and as the aircraft was cleaned up and optimized, speeds kept increasing. 390 miles per hour, 400 miles per hour. The Mustang was proving to be significantly faster than the Spitfire, faster than the Bf 109, faster than any other contemporary fighter, except the German F-1 190, which wouldn't enter service until 1941. And the range was extraordinary. Most fighters of 1940 had combat ranges of 300 miles, 400 miles. The Mustang, with its efficient aerodynamics and with the fuel capacity those efficient aerodynamics allowed, could fly over 750 miles, nearly double the range of contemporary fighters. With external drop tanks, range could be extended to over 1,600 miles, making the Mustang potentially capable of escorting bombers on missions deep into enemy territory. Engineers examining the performance data were particularly interested in the radiator installation. Drag measurements suggested the ventral scoop was creating far less drag than conventional radiator installations. It wasn't clear if true Meredith effect thrust was being achieved. The measurements weren't precise enough to detect small net thrust, but at minimum, the installation was achieving near zero drag, which was itself revolutionary. The Mustang's speed advantage wasn't solely due to the radiator. The laminar flow wing was working as designed, maintaining laminar flow over substantial portions of the wing surface, and creating significantly less drag than conventional wing designs. The overall aerodynamic cleanliness of the design, the attention to every detail that might create drag, contributed to the performance. But the radiator installation was a crucial element that made the Mustang's performance possible. The British received their first Mustangs in October 1941, and RAF pilots were immediately impressed. The aircraft was faster than their Spitfires, had better range, had excellent visibility from the bubble canopy, and handled beautifully at low and medium altitudes. But there was a problem that would limit the Mustang's effectiveness for the next 2 years: the Allison engine. The Allison V1710 was a good engine at low and medium altitudes, up to about 15,000 feet. It performed excellently, and gave the Mustang impressive speed and power. But above 15,000 feet, performance dropped off dramatically. The Allison's single-stage, single-speed supercharger couldn't compress enough air at high altitudes to maintain power. Above 20,000 feet, the Mustang became sluggish and was outperformed by high-altitude fighters like late-model Spitfires and Bf 109s. This limitation meant the RAF used their early Mustangs primarily as low-altitude reconnaissance and ground attack aircraft, rather than as high-altitude fighters. The Mustang excelled in these roles. Its speed and range made it an excellent tactical reconnaissance platform, and its durability and firepower made it effective for ground attack. But it couldn't fulfill the role the Allies desperately needed: a long-range escort fighter capable of protecting heavy bombers flying at 25,000 to 30,000 feet deep into Germany. Meanwhile, the U.S. Army Air Force had also ordered Mustangs, initially designating them as A-36 Apache dive bombers and P-51 fighters. Like the British, American pilots loved the aircraft's handling and performance at low altitude, but were frustrated by its high-altitude limitations. The Mustang seemed to be a fighter with extraordinary potential that was being held back by its engine. The solution came from an unexpected source: a test pilot named Ronald Harker. In April 1942, Harker flew a Mustang at the Rolls-Royce facility in Britain, and was tremendously impressed with the airframe. But he immediately identified the high-altitude performance problem, and had an idea: what if the Mustang was re-engined with the Rolls-Royce Merlin, the superb British engine that powered the Spitfire, and that had a 2-stage 2-speed supercharger, providing excellent high-altitude performance? Harker wrote a report to Rolls-Royce suggesting this engine swap. The idea made its way up through military channels, and by late 1942, several Mustangs had been experimentally fitted with Merlin engines. The results were extraordinary. The Merlin-powered Mustang was not just good at high altitude, it was phenomenal. Maximum speed increased from about 390 miles per hour with the Allison to over 440 miles per hour with the Merlin. Service ceiling increased from 31,000 feet to over 41,000 feet. The Mustang with a Merlin engine was suddenly the fastest fighter in the world at most altitudes, and it could maintain that performance from sea level to over 40,000 feet. What made this transformation even more remarkable was that Edgar Schmued's ventral radiator design, which had been optimized for the Allison engine, worked even better with the more powerful Merlin. The Merlin generated more heat than the Allison, which meant more thermal energy was being absorbed by the cooling air passing through the radiator. More heat meant more expansion of the cooling air, which meant more velocity increase in the exhaust section of the radiator duct. The Meredith effect became more pronounced with the Merlin installation. Engineers measuring the Merlin-powered Mustang's performance were astonished to find that at certain speeds and altitudes, the ventral radiator installation appeared to be producing slight net thrust rather than drag. It wasn't enough thrust to be measurable as actual forward acceleration. We're talking about perhaps 50 miles 100 pounds of thrust from a system that might otherwise have created 200 miles 300 pounds of drag in a conventional installation. But the fact that a cooling system could contribute thrust rather than subtract speed was revolutionary. The Merlin engine was built under license in the United States by Packard, designated the V1650. North American began producing Merlin-powered Mustangs in quantity, designated P-51B and P-51C depending on which factory built them. These aircraft began reaching combat units in late 1943, and they immediately transformed the air war over Europe. The U.S. 8th Air Force had been conducting daylight strategic bombing raids against Germany using B-17 and B-24 heavy bombers. These raids were suffering catastrophic losses on some missions. 10 to 20% of the attacking bombers were being shot down by German fighters. The problem was that existing Allied fighters didn't have the range to escort the bombers all the way to targets deep in Germany. Bombers would fly the first part of the mission with P-47 Thunderbolt escorts, but the P-47Cs would have to turn back when they reached their fuel limits. Bombers would then be unescorted for hundreds of miles over German territory, and German fighters would swarm them. The P-51 Mustang changed this equation completely. With internal fuel and 2 external drop tanks, a P-51 could fly from bases in England to Berlin and back over 1,600 miles total mission distance, and still have fuel remaining for combat. No other fighter in the world had anything close to this range, and the P-51 could fight on even terms with any German fighter it encountered. It was faster than the B-5109 at all altitudes. It was faster than the FW-190 above 15,000 feet, and could outturn it in prolonged dogfights. The first long-range escort mission to Berlin occurred on March 4, 1944. 8th Air Force bombers struck targets in Berlin escorted by P-51 Mustangs for the entire mission, the first time Allied fighters had accompanied bombers all the way to the German capital. German fighter pilots were shocked to encounter American long-range fighters so deep inside Germany. They had assumed such range was impossible for a single-engine fighter. The impact on bomber losses was immediate and dramatic. Missions that might have suffered 10% losses when unescorted suffered 2 to 3% losses with P-51 escort. The Luftwaffe, which had been mauling unescorted bomber formations, suddenly found itself fighting for survival against swarms of long-range fighters that could engage them anywhere over Germany. By mid-1944, the Luftwaffe was suffering unsustainable losses and was being driven from the skies over its own territory. German pilots who encountered P-51s reported the aircraft's performance with a mixture of respect and frustration. The P-51 was fast enough that it was difficult to escape from. It had good acceleration and climb rate. It could turn well in sustained dogfights. And critically, when German pilots damaged a P-51 and thought they had scored a kill, they would often see the Mustang continue flying, absorbing damage that would have downed other aircraft, and making it back to England. This durability was partly due to the Mustang's structure. It was robustly built and could take battle damage. But it was also due to the ventral radiator location. In fighters like the Spitfire or Bf-109 where the radiator was located under the nose or in the wings, any damage to the cooling system would result in rapid coolant loss and engine overheating, forcing the pilot to shut down the engine and crash land or bail out. But the Mustang's radiator, located well behind the engine under the fuselage, was less likely to be hit by forward-firing guns. And even if the radiator was damaged, the pilot often had enough time to gain altitude and glide toward friendly territory before the engine overheated. German engineers examined captured P-51s and tried to understand the source of its performance. They were particularly interested in the laminar flow wing and the ventral radiator installation. Messerschmitt engineers attempted to incorporate similar features into improved versions of the Bf-109, but they found that the precision manufacturing required for laminar flow wings was beyond what German industry could achieve under wartime conditions. The radiator design was studied but never successfully copied, partly because German engineers didn't fully understand the Meredith effect principles involved, and partly because adapting the design to existing German fighters would have required extensive redesign. What made the Mustang's radiator installation particularly effective was how it integrated with the overall aircraft design. The ventral scoop was positioned in an area where the fuselage was already expanding. The fuselage was wider at the scoop location than ahead of it. This meant the scoop could be blended into the natural shape of the fuselage with minimal additional cross-sectional area. The intake was positioned to receive air from below the aircraft where it was relatively cool and undisturbed by the fuselage boundary layer. Inside the scoop, the air flowed through a carefully designed duct that had multiple functions. First, it slowed and compressed the incoming air, converting its kinetic energy into static pressure. This high-pressure air then flowed through the radiator matrix, absorbing heat from the engine coolant. The heated air then entered the exhaust section of the duct, which was shaped as a converging-diverging nozzle, essentially a de Laval nozzle like those used in rocket engines, but operating at subsonic speeds. In this exhaust section, the heated, expanded air was accelerated. The physics involved are straightforward thermodynamics. When air is heated at constant pressure, it expands. If that expanded air is then allowed to flow through a properly shaped nozzle, it can be accelerated to velocities higher than its original speed. The exhaust of the Mustang's radiator system was exiting at a higher velocity than the intake air, which meant momentum was being added to the airstream thrust. The amount of thrust generated was dependent on several factors: the temperature increase of the cooling air, which depended on engine power settings and coolant temperature, the efficiency of the radiator heat transfer, the mass flow rate of air through the system, which increased with aircraft speed, and the design of the exhaust nozzle. At cruise power settings around 350 to 400 miles per hour, the system was achieving approximately zero net drag. Thrust from the exhaust was balancing drag from the intake and radiator. At higher power settings or higher speeds, net thrust of perhaps 50 mighties 100 pounds was being generated. This might not sound like much thrust from a system that was avoiding perhaps 200 mighties 300 pounds of drag from a conventional radiator installation, but in aircraft performance, every pound counts. A conventional radiator installation might reduce an aircraft's maximum speed by 15 to 20 miles per hour. The Mustang's installation was adding no drag and potentially slight thrust, which translated to a speed advantage of 20 to 30 miles per hour over what the aircraft would have achieved with a conventional radiator. In combat, that speed difference could mean the difference between catching an enemy or being caught, between escaping an engagement or being shot down. The later P-51D model, which entered service in mid-1944, refined the radiator installation further and added a bubble canopy that gave pilots exceptional visibility. The P-51D became the definitive Mustang variant and was produced in larger numbers than any other variant. Over 8,000 P-51Ds were built. This model achieved a maximum speed of 437 miles per hour at 25,000 feet, making it faster than any other piston engine fighter in mass production except for a few late-war German aircraft that were produced in tiny numbers. By 1945, the P-51 Mustang had achieved air superiority over Germany and was escorting bombers to any target in German-held territory. In the Pacific Theater, P-51s based on Iwo Jima were escorting B-29 Superfortress bombers on missions to Japan, missions of over 1,500 miles that no other fighter could have flown. The Mustang had proven that Edgar Schmued's radical radiator design wasn't just functional, it was a key element in creating the best fighter aircraft of World War II. Post-war analysis by NACA engineers confirmed that the Mustang's ventral radiator installation was achieving something close to the theoretical Meredith effect. Wind tunnel tests and flight tests with instrumented aircraft measured the pressures and temperatures throughout the radiator duct and confirmed that the exhaust air was exiting at higher velocity than the intake air. The cooling system that everyone assumed would create drag was instead approaching thrust. The significance of this achievement extended beyond World War II. The Mustang's radiator design influenced post-war aircraft development and became a standard example in aerospace engineering textbooks of how careful attention to thermodynamics and fluid dynamics could turn a necessary component into a performance advantage. Modern aircraft still use variations of the Meredith effect in their cooling system designs, though jet engines have different cooling requirements than piston engines. The irony is that the Meredith effect, which made such a difference to the Mustang's performance, was almost invisible. Looking at a P-51, the ventral scoop under the fuselage is noticeable but not dramatic. It doesn't look revolutionary. It looks like a practical solution to the problem of cooling system placement, which it was. But it was also a masterpiece of aerodynamic engineering that contributed significantly to making the Mustang the fastest piston engine fighter of its era. Edgar Schmued and his team at North American Aviation had taken a theoretical paper that most engineers dismissed as impractical and turned it into reality. They had designed, built, tested, and proven that a radiator could approach zero drag rather than being a significant source of drag. They had done this under extreme time pressure. The entire Mustang was designed in 120 days, and they had gotten it right the first time without years of development and testing that fighter designs normally required. The ventral radiator installation exemplifies how the Mustang succeeded by questioning assumptions, by applying the latest scientific research, by refusing to accept that this is just how it's done, and by executing a radical design with precision and skill. Every aircraft designer in 1940 knew that radiators created drag. Edgar Schmued proved that they didn't have to. The legacy of the Mustang's radiator design continues in modern aircraft engineering. When engineers design cooling systems for high-performance aircraft, they reference the Mustang's installation as an example of how to minimize cooling drag or even create thrust recovery. The principles Schmued applied, careful duct design, efficient heat transfer, optimized exhaust acceleration, are still fundamental to aircraft cooling system design today. The Mustang went on to serve long after World War II ended. It flew combat missions in Korea, served with air forces around the world into the 1980s, and remains a popular aircraft at air shows today. Over 15,000 Mustangs were built in total, and hundreds survive in flying condition. When spectators watch a P-51 perform at an air show, flying at 400 plus mph just hundreds of feet above the ground, they're watching an aircraft whose performance was made possible by a radiator that broke the rules everyone thought were unbreakable. The story of the Mustang's radiator is a reminder that in engineering, the impossible is often just something nobody has figured out how to do yet. It's a reminder that questioning assumptions and applying scientific principles can create breakthroughs that change everything. And it's a reminder that sometimes the most important innovations are the ones that are almost invisible, the careful design choices and engineering excellence that turn a good design into a great one. Edgar Schmued and his team proved that with enough knowledge, enough skill, and enough willingness to challenge conventional thinking, you could take a necessary evil like a radiator and turn it into a performance advantage. They proved that the laws of physics, properly understood and applied, could produce results that seemed impossible to those who didn't understand them. They proved that 120 days was enough time to design a revolutionary aircraft if you had the right people, the right approach, and the courage to try something nobody else had successfully done. The P-51 Mustang's ventral radiator, mounted under the fuselage where Edgar Schmued placed it in 1940, contributed to creating the fastest, longest-ranged and most effective fighter aircraft of World War II. It helped win air superiority over Germany, enabled the strategic bombing campaign that crippled German war production, and saved countless bomber crews who would have been lost without fighter escort. And it did all of this while approaching zero drag or even creating slight thrust from a component that everyone else accepted would slow their aircraft down. That's not just good engineering, that's genius.